I still owe you the promised proof of Scarves' theorem. So let's state the theorem again. Let S be a d-dimensional simplex which is divided into subsimplices of diameter at most delta. Let F be a function from S to S and color every vertex V of every subsimplex according to the rules from the proof of Brouwer's fixed point theorem. So that means that if V has color J, then f of Vj is less or equal to Vj. Now, if delta is chosen such that delta is less or equal to alpha divided by 2d, and for all x and y from S that have a distance of at most delta, we have that the images of x and y have a distance of at most alpha divided by 2d, then any point in a fully colored subsimplex is an alpha approximate fixed point of the function f. And the proof goes as follows. Consider any point x, which consists of d plus 1 values, x1 to xd plus 1, that are all non-negative and sum up to 1. And so x is a point in a fully colored subsimplex. Now we want to prove that this x is an alpha approximate fixed point. For this, it's enough to show that for each j, the difference between the jth component of f of x and the jth component of x itself is at most alpha divided by d and at least minus alpha. And if this difference is at most alpha divided by d, it means in particular that it's at most alpha. So the difference in the jth coordinate between x and f of x is at most alpha. And that means, if this is true for every coordinate, that the maximum norm of the difference is at most alpha. And that means x is an alpha approximate fixed point. So this is exactly what we need. So how do we show this for each j? Well, just fix one j and we will try to prove it for such a fixed j. So the first step is to prove the first inequality here, so to show that the difference is at most alpha divided by d. Now, let y be a corner of a subsimplex containing x. And particularly, let it be a corner that has color j. Remember, this corner exists because x lies in a fully colored subsimplex, so all the colors exist in some corner. So we can find a corner that has color j and let y be that corner. And in particular, this means that the jth component of f of y is less or equal to yj. So this was part of the coloring rule from Brouwer's fixed point theorem. Now, because y and x are part of the same subsimplex, and the subsimplices have a diameter of at most delta, we know that x and y also have a distance of at most delta. And that just means that each component of x and y can be at most delta apart. So it means in particular that yj minus xj is at most delta. But it means something else as well. If we check the conditions in the statement of the Scarves theorem, then we see that if the distance between x and y is at most delta, it must follow that the difference of the images of x and y, so f of x minus f of y, the norm of that is at most alpha divided by 2d. And so we know that this holds as well. Okay, so we are interested in bounding the jth component of f of x minus the jth component of x from above. So let's just write this down. And now I use a common trick. I just expand this expression by adding something, but then subtracting the same thing. And what I'm adding and subtracting is just the jth component of f of y. Of course, this doesn't change anything. Now, the first part here we've just discussed is actually less or equal alpha divided by 2d. And the jth component of f of y, we've seen that before, is less or equal to yj. And now we have yj minus xj is actually less or equal to delta, and we've discussed that before. So I use all those previous inequalities and plug this in the right way, and we get that this whole expression is at most alpha divided by 2d plus delta. Now, alpha divided by 2d plus delta, we just plug in the bound for delta that we have from the statement of the theorem, right? We required that delta is at most alpha divided by 2d, so I plug that inequality in, and I get that this whole thing is less or equal to alpha divided by 2d plus alpha divided by 2d. And that's just equal alpha divided by d. And this is exactly what we wanted to show. It remains to show the second part, where we show that minus alpha is less or equal this difference. And for this, we just use the first part again. So we just write this down. So the jth component of f of x minus the jth component of x is equal what? Well, we know that all these components of x and also all the components of f of x have to sum up to 1. And we can use this fact, because what this means is that one component is equal to 1 minus the sum of all the other components. So the jth component of f of x is in fact equal to 1 minus the sum over all other components of f of x. And the same is true for xj. xj is just equal to 1 minus the sum of all the other components of x. And now we just need to simplify. The 1 cancels out, and then we just have to be a bit careful about the signs here. And what we simply get is the sum over xi minus f of xi over all I that are not equal to j. And from the first step, we know that xi minus f of xi is at least minus alpha divided by d. Right? The inequalities flips around because of the negative sign here. And so we just get the sum over all i's that are not equal to j of minus alpha divided by d. And because there are d components in these vectors that are different from the jth component, we just get minus alpha. And this is exactly what we needed. We have f of xj minus xj is at least minus alpha, which is what we wanted to show. And this completes the proof of Scarves' theorem.